Good morning, students. So today, crash course day number 20. And what we are going to do, in the last class, we started current electricity. Okay, a little bit. So we are continuing with that. So let's see. The first topic that we are starting today with is drift velocity. Now, drift velocity is what? Drift velocity is the velocity gained by the electron once you are applying electric field across it, or you are applying potential difference across a conductor. Then electron will start drifting towards one side. Otherwise, electrons are doing their random motion, okay, and their net displacement is zero. But because you have applied the electric field, electrons will start drifting towards one side. So the velocity gained by them is called drift velocity. So let's see then what it is. If I can say that this is a conductor, okay, there is a conductor like this, and we have applied a potential difference. Let's say here is V1 and here is V2, and we say V1 is greater than V2. Okay, V1 is greater than V2. So electric field is in this direction. Electric field is in this direction. Let's assume that there is one electron over here. That is what we are going to observe. So where electron will move? Electron always moves opposite to the direction of electric field. Like this it's moving. Okay, and we are going to talk about this motion only. We are not talking about its random motion at all. Okay, so because of this one, there is a force acting on it. What is that? F equal to E into E. And because of that, there will be acceleration. So we will say mass into acceleration is equal to QE. So acceleration is QE. Q is E over here, okay? EE by M. Before application of electric field, what was the velocity in this direction for this electron? 0. So U is 0. Okay, is the acceleration constant? You said yes. So equation of continuity can be applied? Yes. So V equal to U plus AT. Okay, so V equal to 0 plus EE by M into T. This is the velocity after time T. Okay, so this is what we are saying is drift velocity here. EET by M. Okay, so is drift velocity directly proportional to electric field? Answer is yes. We can see that over here. That drift velocity is directly proportional to electric field. Correct? This is there. Now, we should be knowing, now we all know that current is because of the motion of electron. Okay, this is the drift velocity also we have got. So, is there any relation with current over here? That also we can do. Okay, so if I can move this a little over here. Okay, let's move it a little here. Right, we moved it. But this also has moved. So we can, oh God, okay, fine, let it be here. Right, now what? Now we want to see current. Okay, fine. Current is what? Current is basically charge by time. Right, flow of charge per unit time. Q is what? Q is in terms of electrons. So we'll say N into E by T. What is N? N I'll write in capital letters here. Okay. Number of electrons that are flowing per unit time. Right. Now if conductor is this. Okay. Now its area we can consider this cross section area. Let's say is A. Okay. And I am assuming there are N electrons per unit volume. There are N electrons per unit volume. N electrons per unit volume. Okay. So what we can say? This is total N electrons which are moving. But how many electrons are there in per unit volume? N. Okay. So N actually is equal to, okay, N by V. Okay. So N value is what? You say NV. So can we put it over here? Yes. We can write N V E by T. Now what is this? This is velocity? No, this is volume. Okay. This is volume here. So volume means what? A E by T into into what? The little distance that it has moved. Volume doesn't mean the total length of this one I am going to take. No, because electron is moving very little. So how much it has moved? Suppose x. So x. So what we can write this as? I equal to n e a x by t. X by t will be called as drift velocity. So I is equal to n e a v d. Very, very important relation. This is also important and this is also important. Okay, drift velocity in terms of electric field is this, and current and drift velocity relation is this. So I equal to n e a v d. Okay. Then what? Then there is a question then. Okay, we got a relation, so let's have a question. So this is a conductor. Okay, conductor shape is like this. And we can see that this is a variable cross section conductor. Okay, what is he asking? He is asking electric field ratio. Okay, so we know that if there is a current over here, if there is current I, here also current will be I. Current do not change. Same current will be flowing. Okay, so we will say that I at A is equal to I at B. Then what you can say? N E into area at this section. Okay, into V at A is equal to N E area at section B into V at section. Now N, because it's the same material, the number of electrons per unit volume will be same only. This is electron, so electron also cancel. So area at A into velocity at B. Which velocity? Drift. So drift velocity, what we can write? What we can write? Q E by M into T. So E A by M into T. Now this is all for electron. So this mass, this E and this T. Okay, they will be same here also. This is A of V. Now here is EB into T by M. So ETM gets cancelled. What they want? EA by EB. So EA by EB actually is coming as area at B by area at A. This is our answer. Okay, so remember that if the same material is there, we can say that number of electrons or electron density is same. Okay. Alright. Again one more question like that. Okay, here area is given 3A, here area is given A. And it is also given that drift velocity at A is equal to drift velocity at B. Point NA by NB, that means he is saying that number of electrons per unit volumes are different here. Drift velocity is given same. Okay, so what we can do? Again, current at least will be same only, no? Okay, so I at A equal to I at B. What is I? NEA VD. So NA into area at A NEA VD. Now VD is same at both, so we don't have any problem, right? Okay, here what? NB, area at B, VD at B. Okay, then E. So E is cancelled. So VD and VD cancel because it's given same. It is equal. That's it. NA by NB equal to what? NA by NB equal to area of B by area of A. Area of B is given what? Area of B is given A and area of A is given 3A. So A by 3A, that is 1 by 3. This question's answer. Okay, fine. Let's see then. Resistance or resistor is conductor or insulator? Resistor is conductor. Okay, resistor is conductor. How can we say? We can say because through this one current is passing. Through this one current is passing or not passing? Passing. Electrons are on its surface or not? Yes. So that means what it is? A conductor is having resistance. It offers resistance to the flow of current. Why? Because there are too many electrons, and when electrons are moving, they are colliding. It's not a free motion of electrons. So because they are colliding, they are opposing. Okay? There is opposition. That's what we are calling as resistance. So definitely resistor is a conductor. Okay? Relation between resistance and temperature. Okay? resistance and relation between resistance and temperature, how to find? Now, one relation about resistance we already know, resistance equal to R equal to rho L by A. Okay, what is rho? Rho is actually resistivity, which is actually property of the material, okay, due to which it opposes the flow of current, right? L is length of conductor, and A is cross section area. Okay, but in this relation we don't have any temperature at all. But we know that temperature is, R depends on temperature. When we are increasing the temperature, R also increases. So there is nothing like that. How to find that then? So little while ago we got to this relation, I equal to NEA VD. Okay, now again one more time, if you are going to make a conductor here, this is a conductor. Okay, now suppose that here potential is V and here potential is 0. That means potential difference across this is 0. This is L, length, and area of cross section we take as A. Okay, so this I value I am writing as V by R. From which law? Ohm's law. Ohm's law we have seen already, right? So I equal to V by R. Then here E is here, A is here, VD. Now VD I am converting in terms of electric field. So what it is? E by M into T. Okay. So V by R equal to NE square AT by M into E. Now E I am writing in terms of potential difference. What we can write? E is equal to dV by dr we know. dV here is what? V, and dr is what? L. Put it. V by M. So this V and this V you can see is cancelled. So R value that I am getting is ML by NE square A T. So here mass is constant, right? Number of electrons per unit volume constant, electrons charge constant, area of cross section constant. Okay. Now we want that how resistance changes with temperature or relation with temperature. So what happens when we are increasing the temperature? Okay, this is relation. Okay, this is relation first. Now if you are increasing the temperature, random motion of electrons increases. When random motion of electrons increases, they collide frequently. This T is what? This T is relaxation time. Okay, this T is relaxation time. Relaxation time means what? Relaxation time means the time between two successive collisions of electrons. Time between two successive collision of electron. Successive collision of electron. Okay, so what we are saying now, once the temperature is increased, speed of electrons increase. Which speed? Random motion speed. So because of that they collide more and more. So because of that this T decreases. You increase the temperature, T decreased, and if T decreased, R increases. Okay, so that's why we can say that relation between resistance and temperature is what? If temperature is increased, resistance also increases. So what relation we follow? What is the relation that we follow actually for that? For that we follow a relation which says, okay, that we'll in thermal coefficient we will study anyhow. So okay, for the timing this much only, R equal to ML by NE square AT, where here this is relaxation time. If temperature is increased, this decreases means resistance increases. Okay, and in this one, if suppose I want to find what is the value of rho, then in place of R you write, rho L by A. Okay, so here rho L by A what we are keeping. Then what it is here, ML by NE square T. L and A here gets cancelled. So M by NE square T is resistivity. M by NE square T. Okay, so if temperature is increased, this T decreases, the rho also increases. So here you can write resistivity also increases. Clear? Okay, let's see. Now there is a question over here. One conductor we have kept whose resistance is 12 ohm and length is 3 ohm. We are cutting it into two. This is 1 meter, this is 2 meter. Now what we have to find? Ratio of the resistances. Okay, so what we can say over here? How to solve this? So we can say resistance per unit length is how much? What is resistance per unit length? R by L. The R by L is 12 by 3. That is 4 ohm per meter. So this is 1 meter. So its resistance is what? 4. And this is 2 meters. So its resistance is what? 8. That's it. Resistance per unit length is 4 ohm. 4 ohm and 8 ohm, R1 by R2. That's it, over 1 by 2. Clear? Okay, one more. So what it says is, there is conductor of length L and area A. If length is stretched n times, then what happens to resistance? Okay. So we are increasing its length to n times. So when you are increasing its length to n times, what will happen? It will become thin. Thin means its cross section area is going to decrease. What is going to decrease? Cross section area is going to decrease. Anything remains constant? Yes, volume. Volume will be constant. Okay, so we will say that volume initial equal to volume final. What is volume initial? Say A into L. What is volume final? We know that length is going to become n times. NL. What is this area? We don't know. So let's say A1. L gets cancelled. So A1 actually has become A by N. Then okay. Okay, this is important. Now initial resistance is what? Say initial resistance, you can say rho L by A. Resistivity we assumed. Resistivity is not going to change even if you are changing its length, because that's a property of the medium. Okay. So R1 is what now? R1 is rho into new length. What is new length? New length is ln or NL by new area. Now new area means A1. What is that? A by N. So A by N. What we are getting? Rho L by A into N square. So that means R1 actually is N square R. So if you are going to increase the length by N times, then the new resistance will be N square times the initial resistance. Okay. Next, if the length is compressed 1 by N times, then similar thing, similar way we will solve that one. Okay. So solution says volume is constant, volume initial equal to volume final. What is volume initial? A into L. What is going to be volume final? We know that length is going to become 1 by N times. Okay, so this is L by N. What is its area? We don't know. So A1. L gets cancelled. So A1 is becoming NA. Okay, fine. Now, initial value of resistance is what? Rho L by A. So R1 is what? Rho into new length. New length is what? L by N. New area is NA. So this is rho L by A into 1 by N square. That means new resistance is 1 by N square. Initial resistance. Okay, there when you are increasing its length to N times, it becomes N square R. If you are decreasing its length and making it 1 by N times, then resistance become 1 by N square times. Okay. Alright. What this is now? Thermal coefficient of resistance, right? So thermal coefficient of resistance we see. In thermal properties, we saw thermal coefficient of length, linear coefficient of thermal expansion, or areal coefficient or volumetric coefficient. Here it is thermal expansion of resistance. Same kind of a thing. Alpha only we define it as. Alpha is what actually? Say delta R by R delta T. There how we used to define alpha is equal to delta L by L delta T. Here it is delta R because it's related to resistance. So alpha equal to delta R by R delta T. Okay. Then R final equal to R initial into 1 plus alpha delta T. R final equal to R initial into 1 plus alpha delta T. So this relation we have to remember. Alpha's unit is what? Same, 1 by Kelvin or per Kelvin. Okay. Let's see, few questions we'll solve. What objects have alpha positive and negative? Okay, before that we should know what objects will have alpha positive and negative. So those objects which on increasing the temperature, the resistance increases, alpha is positive. Now question is, what are those objects? Conductors. Conductors. Okay. Then which one will have alpha negative? When on increasing the temperature, resistance goes down. Their alpha is negative. What are those? Semiconductors, and insulators. Okay, and insulators. So if we increase the temperature, resistance decreases, and if we decrease the temperature, resistance increases. Whereas here, direct proportionality is there. Direct proportionality means alpha positive, and if suppose that there is, I should not say inverse proportionality, but if temperature is increasing and resistance decreasing, then we can say alpha is negative. Okay. Alright. Then, okay, there is a question now. R at 0 degree centigrade is 20 ohm, R alpha is 0.01 per Kelvin, and you have to find R60. Direct formula based question, right? So solution, R at 60 equal to R at 0 into 1 plus alpha delta T. That's it. So this is what we are finding. This is 20. This is 1 plus alpha value 1 by 100 into from 0 to 60. So this is 60. Okay. So this is 6 by 10, that is 0.6, 1.6 into 20. That is 32. That's all. Okay, that's all. Direct formula based question. Put the value, get the answer. Okay, next one. R at 0 is 80, R at 80 is 140, R at 20 is what? Now in this one, they can ask you alpha also. So if they are asking alpha, then what do you do? These two relations we have, we can write R at 80 like the previous question. R at 80 equal to R at 0 into 1 plus alpha delta T. This is given, this is given. Can we get alpha value? Yes, obviously. This is 140, this is 80. This is 1 plus alpha, and here is how much? 80. So this is here what? Is cancelled, 14 by 8. 14 by 8 minus 1 equal to 80 alpha. So this is 6 by 8. 6 by 8 into 8. That will be alpha value. Then again we can write for this one R20 equal to R at 0 into 1 plus alpha t, delta t. We can do that. If they are asking alpha value, do like this. If they are asking only this value, then we have another formula. How we did in the case of thermal properties. The temperature scale was there. There I told you. Okay, exactly same thing we can do here. What is that exactly same thing? Exactly same thing is R20 we want. So I'll be writing R20 minus R at 0 by highest temperature R at 80 minus R at 0. This should be constant. Now their values I can write this side. So R at 20 we are calculating. So here R20 minus R0, R80 minus R0. Here what? Temperatures you write. 20 minus 0 by 80 minus 0. That is it. This side resistances, this side temperature. If you remember, same thing we did in thermal properties. Here we wrote length, here we wrote temperature. Okay. So R at 20 we are calculating. So let it be like this only. R at 0 given is 80. Here 140, here 80, and here is 20. Already we have written. So 20 minus 0 by 80, that is 1 by 4. Okay, then here is what? R at 20 we are finding minus 80. 140 minus 80 is 60 equal to 1 by 4. This is 15. So R20 minus 80 equal to 15. So R at 20 is what? 95. 95 ohm. Okay, this is 95 ohm. R at 20 is 95. That's all. Okay, so this is a lot smaller as compared to this, because here already you have written 4 steps, then 2-3 steps more you will write, 7-8 steps, whereas this is in 3 steps. Okay, so this is easier. As again I am saying, in thermal properties you have seen the same thing. Okay, only difference was here was length, right? Okay. If length of a conductor increases by 0.1%, then resistance increases by length of conductor. Okay, now a little while ago we said that if length is increased, length becomes n times, then resistance becomes n square times. We have written already. Okay. Okay, so resistance is directly proportional to, we can say, what they are asking, resistance only. Yeah. Resistance is directly proportional to what? Or resistance final equal to what? It becomes n square R initial. Yes or no? N square R initial. Okay. What we can say finally here, because he is asking length increases by 0.1%. Do we have any relation with length? Let's go back and check what was the relation. Where it is. Yeah. See. This was the relation. So R1 equal to n square R. But in this one, do we have any relation with the length? Because without length, how can we do? Okay. So here I am saying that in this one, can we do something like this? That R is actually proportional to L square. Because you have increased n times. So resistance also becomes n square times. Length we increase n times, so resistance becomes n square times. So R is actually, we can say, proportional to L square. Okay, is proportional to n square. So here we can say R is proportional to L square. Okay. Certain things are also there, that because proportionality I have used, that means all those things which are there are constants. Okay. So now we can write in errors we have learned, dr by R will be equal to what? 2 dl by L. Okay, so this is percentage change and this is also percentage change. So here percentage change is 0.1%. So resistance changes by 0.2%. Okay, if length increases or changes by 0.1%, then resistance changes by 0.2%, because the relation is like this. If you are increasing the length, then if you decrease the length, then 1 by, right? Okay, combination of resistances. Combination of resistances means series and parallel, right? So series connection. So here is, let's say, R1, this is R2, and they are connected with a battery like this. Okay, now what happens? We all know that what battery does. Okay, the battery gives energy to the charge so that it can move. What is this R1 and what is this R2? R1 and R2 basically represents, suppose appliance are there. This is bulb and this is fan. So what this charge which is going from here will do? It will give energy to this one also, energy to this one also. And then it will come back over here. So whatever energy is given by the battery to this, some is spent over here, some is spent over here. So energy given to this one we are representing in terms of potential drop here and potential drop here. Total energy given to it in terms of potential is V. Here dropped V1, here dropped V2. Actually, in terms of energy, if you want to write, energy given to the electron is EV. Here dropped EV1 and here dropped EV2. So what you can write? V equal to V1 plus V2. That's what we write normally. Okay, V equal to V1 plus V2. Okay, what is V? We can say IR. What is V1? IR1. What is V2? IR2. How IR1, IR2? Because they are connected in series, so same current will flow. Same current will flow throughout. Because we can consider that two wires are connected together, right? So same current will pass. Just like two pipes are connected in series. So whatever the flow of water from this one, same will be the flow of water through this one, right? So current is same. So what we got here? R equal to R1 plus R. This is what we do in series. Okay, now important thing here is what is V1? Say V1 is IR1. V1 is IR1, but we have to find what is its value. Say IR1, so V1. I means what? I means is V by R. I means V by R. So V by R into R1. So this is V by R1 plus R2. R is what? R1 plus R2 into R. That's V1 value. Same way, V2 value, IR2. What is I? V by R1 plus R2 into R2. So this is how we can find V1 and V2. That is the potential drop here. Now suppose the question asks you what is potential here then. Suppose we have to find potential here. Then if suppose I consider potential here is 0 and potential here is V. Then because here is no resistance shown, we can say that here also potential is V and here potential is 0. So here dropped how much? V1. So here will be what potential? Here will be V minus V1. Here will be V minus V1 and here it will become 0. Okay. So remember that. If they ask what is the potential here, it's V minus V1. Right. Let's see parallel connection. A parallel connection means when potential difference across the two capacitors is same. So connection is something like this. Okay, here is battery. This is R1, this is R2. Now you can say that if suppose same thing we say this is V and this is 0, then here is V. So here is also V and here is also V and here is 0, 0, 0. So potential difference across both the resistor is same, is called parallel connection. Okay, then from this battery, let's say current is I going. That means the flow of charge. Okay, its magnitude is I. So I is over here. This comes junction. Let's say current goes here is I1 and here is goes I2. So first thing that is asked from us is what is I1 and I2? How to find that? How to find I1 and I2? So I1 basically is what? I1 is actually V by R1. And this is V now. Here across this is what potential? V only. V by R1. Correct? So it's V by R1. I2 is V by R2. Correct. But I don't want to write it into this now. I want I1 in terms of I, not in terms of V. Okay. So what is V? So V equal to this V only we have to replace now. So V equal to what? I into R1 plus R2. Okay, I haven't found it yet. Wait. Parallel, no. Parallel, I didn't find no net resistance yet. So how to find it? Now I equal to I1 plus I2. First do that one, then we will do. I1 is, I have written already V by R1, so place it here. This is V by R2 and this will be written as V by R. So what is resistance? 1 by R equal to 1 by R1 plus 1 by R2. Okay, so R is equal to R1 R2 by R1 plus R2. Correct? Simple. Now, as I was saying that I1 I want in terms of I. So V only we have to replace. Okay, so what is this? I equal to V by R. So that means V equal to IR. No? V equal to what? IR. So I1 in place of V what? I R by R1. Correct? No. Correct. And what is R? R is this. Place it. I by R1 into R1 R2 by R1 plus R2. R1 gets cancelled. So we are getting I1 value is I R2 by R1 plus R2. I1 value is I R2 by R1 plus R2. And I2 value obviously will become I R1 by R1 plus R2. A very similar relation is there, not much of the difference. V1 you see, V R1 by R1 plus R2. So here V1 in terms of V by R1 plus R2. Here I1, I by R1 plus R2. But since I is inversely proportional to resistance, in when we are finding I1, you are writing R2 here. Whereas here, when you are finding V1, you are writing R1 only. V2, that means you are writing R2. Whereas here, I1, here is R2, here is I2, here is R1. Inverse proportionality here, direct proportionality. Okay, this is important actually. If we can remember, it's okay. Otherwise, I'll tell you one more method. Okay. Let's move ahead. A piece of wire of resistance 4 ohm is bent through 180 degree at its midpoint and two halves are welded together. Then the resistance is. Okay. Alright. So there is a wire. Okay. There is a wire. I'll try to make it little thicker. So there is a wire like this. But its thickness is not increased. Okay. So through pen only it will increase. Okay, fine. Yes. So this is a wire. Now what he says is, it is bent through 180 degrees at its middle point. Now middle point is this. So from here we are going to bend it. Something like this. Like this. Okay. Now we are welding it. Then what is the resistance? Now if suppose it's 4 ohm. So I know that this is 2 ohm. Oh, okay. Let's decrease it now. What is this? This is 2 ohm. And this also is 2 ohm. Correct? So you bend it together. So now this is 2 ohm and this is also 2 ohm. So what has happened? Now this is actually parallel, right? If suppose this is resistance, earlier it was like this. This is 2 ohm, this is 2 ohm. Earlier, this one. Now what is this? This is 2 ohm and this is 2 ohm. Now this is parallel, no? So parallel means what we have to do? Answer is 1 ohm, right? 1 by R equal to 1 by 2 plus 1 by 2. That is 1. So R equal to 1 ohm. R equal to 1 ohm. Simple. Okay, let's move ahead. Okay, one more time, similar question that we did already, right? Okay, this is one type of a conductor. Its diameter is given d, its diameter is given d by 2. Current I is flowing and he is asking drift velocity over here. Simple question, right? Again, I equal to I at A. Okay, I at A equal to I at B. This is N E area at A and drift velocity at A equal to NE area at B into drift velocity. So this is same because same conductor, this is electron, that is same. So what? VdA by VdB. Okay. So VdA by VdB equal to area at B by area at A. Now area at B. Now its diameter is d by 2. Okay. So diameter is d by 2. So radius is d by 4. Half of this only radius. So pi d by 4 whole square by area at A. Its diameter is d. So radius is d by 2. So pi d by 2 whole square. Pi cancel. This is d square by 16 and this is 4 by d square. Okay. 1 by 4 is the answer. VdA by VdB is 1 by 4. Right? Okay. Combination of resistances. We already done. Series and parallel we have seen. Okay. We already done that. Okay. So wire of length 18 meter is converted into ring. Find resistance between A and B. So its total resistance of this entire wire is 18 meter. Okay. Now what you have done? You have made two sections. This is one section and this is the other section. And he is asking resistance between AB. So what is the meaning of that? It means is you must have connected on battery like this here. So when current goes like this, current is going to divide into two parts like this. This current will go in this way, this current will go in this way. Okay, so this section and this section actually are parallel. They are parallel. Okay, first of all, let's find resistance. What are the resistances? Wire of length 18 meter is connected into ring, converted into ring. Find resistance between AB. So its resistance actually is not given. So let's assume that wire of length 18 meter is converted into ring. Resistance, how much shall we take? R shall we take? Or we can take anything like 40 ohm, wire of 18 meter and 40 ohm. 40 is okay. Fine. Okay. So 18 meter is their wire which is having resistance 40 ohm. Now this is 60 and remaining is 300 degrees. Okay. So 60 degree, basically when you are converting it into a circle is making what angle at the center? 360. So 60 degree is what? 1/6 of that. 1/6 of that. So its resistance will be what? 1/6 of the total. So total is 40. So its resistance will be a 40 by 6 ohm. This is 40 by 6. So remaining this is 300 degrees. This is what? 300 degrees. So 300 degrees means 5 times of this, because this is 60. So this is 5 times of this. So what is its resistance? 200 by 6 ohm. Now this and this both are connected parallelly because both are connected between two ends, A and B. So one resistance here is 200 by 6 and other resistance here is 40 by 6. He is asking total resistance. So 1 by R equal to 1 by R1 plus 1 by R2. That is 6 by 200, because this will be 200 by 6. 6 will go up. Okay. 6 by 200 plus 6 by 40. Take the LCM. LCM can come 200 only. This is 6 and this is 45. So 5 into 6 is 30. So 1 by R. So R equal to what? 200 by 36. We can simplify that. So 200 by 36 is our answer for this question. Okay. Now what is next? Next is general question, series parallel question actually. Okay. So what it is here, what we can do, let's see. What the question is asking. Find IE, I1, I2, V1, V2. Okay. So let's find out I first. What type of connection is this here? If this is end P and this is end Q, let's say. Okay, so this is called parallel connection. because potential difference is Vp minus Vq for this also, here also. Parallel connection. 6 and 3 are connected parallelly. So R will be what? R1 R2 by R1 plus R2. R1 R2, 6 into 3, 18 by 6 plus 3, 9, 18 by 9 is 2. 2 plus 6, 8 ohm. So current is 24 by resistance 8. So I is 3 ampere. That no problem. Now second question is I1 and I2. So if you remember that formula we did, okay, if this is I1 and this is R1, then I1 is equal to IR2 by R1 plus R2. If you remember the formula, well and good. If you don't remember, then what to do? Very simple. I is inversely proportional to R, we know. Right or not? Because V is constant in parallel connection. I is inversely proportional to R. So it means I1 by I2 will be R2 by R1, 100%. That means I1 by I1 plus I2. I1 by I1 plus R2 must be equal to R2 by R1 plus R2. Yes. What is I1 plus I2? I only is getting converted into this I1, I2. So I1 by I is equal to R2 by R1 plus R2. That's all. Over. I1 equal to IR2 by R1 plus R2. Simple. If you don't remember that formula, like this we can solve. Okay. So now let's put it. What is I? 3. So 3 into R2. This is 6. By R1 plus R2 means 9. What's coming? 2. I1 is 2. I2 is 1 ampere, surely, because I equal to I1 plus I2. I is 3. Then what we want? V1 and V2. Now very easy it is. V1 is what? I1 into R. I1 into R. What is I1? 2. And R1? 3. 2 into 3. That is 6 volt. V2 is also 6 volt because they are parallel. 1 into 6. Right. So this is how we can calculate easily I1 and I2 in parallel connection. Okay. Then, all right. A different type of a question. Now what this is? Here you can see there is a wire. And wire has no resistance. It's not shown at least. We know that conductors are always have resistance. But here resistances are shown. Whichever are available, they are shown. Here it's not shown. That means we will say resistanceless. Okay. So if it's resistanceless, and if I say here, if here is B, here is potential at B. So here also if I say potential at B, then here if no resistance is dropped, here also potential will be B only. Here is A, so is here. So here also potential will become A. So across this, what is potential difference? VA minus VB. Across this, VA minus VB. Across this, VA minus VB. That means all three are connected parallelly then. If this is A, then I can write this like this. This is B. Then one more and one more. R. So what we can say? 1 by RAB equal to 1 by R plus 1 by R plus 1 by R. That is 3 by R. So RAB equal to R by 3. Okay. So if there is no resistance given and there is a wire connecting 2 points, then both are at same potential. Alright. Okay. So now what this is? This is actually Wheatstone bridge. What exactly is Wheatstone bridge? Wheatstone bridge we will see. So here only we will see and then we will solve this one. Okay. Wheatstone bridge. What is the concept? concept says if five resistors, 1, 2, 3, 4 and 5. Okay, 5 resistors are connected in such a way that that potential difference at this point and this point is 0. Okay, VA minus VB is 0. That is VA equal to VB. Okay, let's assume this point is P here and this point is Q. Okay, so if VA minus VB is there, that means we can write VP minus VA will be equal to VP minus VB. Perfectly. Right or not? And suppose current is coming from here like this, and here will be I1 and here will be I2. Same way, if here potential is 0, that means potential difference is 0 in this one. Okay, so what will happen? No current will pass through, because for passing the current you require potential difference. We are saying there is no potential difference. So this I1 will continue to move here and I2 will go like this. Because no current will exchange over here. Now we will say that this resistance is useless because current is not passing through this. So whether it is there or not there, it doesn't make any difference. Okay, but VA minus VB equal to 0 and VA equal to VB. Then what is the relation comes out? We get the relation as R1 by R2 equal to R3 by R4. So if R1 by R2 is there and R3 by R4 is there, definitely A and B will be at same potential. That is what Wheatstone bridge says. Understood that? If this is the case, then net resistance will be what? R1 and R3 are in series, R2 and R4 are in series, and then they are in parallel. What is the net resistance here? 1 by RPQ, 1 by R1 plus R3 plus 1 by R2 plus R4. Because these two are in series, then they are parallel. This will be the net resistance. Okay, this is Wheatstone bridge. Again, Wheatstone bridge is saying us that you should have the resistance connected in such a way that here and here potential difference is 0. For here and here potential is same. Check here what we can say. Now here this is C and this is D. Okay, now can we make it like this? Yes, obviously. This point is A. Now between A and C one resistance is there. Say this point is A. Okay. So this is A and C. Then you have one more between A and D. Make it here. A and D. Then you have C and D. So C and D is here. Then you have C and B. And you have D and B also. See, it's very similar diagram. This and this are exactly similar, right? Now see that this is R, this is R, this is R and this is R. So if this by this equal to this by this, that means this is Wheatstone bridge. So that means this is of no use. Remove this resistance from here. So then R and R are in series, R and R are in series. So this is 2R, this is 2R. So it's something like this. This is 2R here and this is also 2R. Both are connected how? Parallelly. The net resistance will be what? R. So RAB will be R. How it came? Okay. 1 by RAB equal to 1 by 2R plus 1 by 2R. That's 2 by 2R. Okay, 2 by 2R means 1 by R. So RAB equal to R. Wheatstone bridge. Okay. Right. See this now. Now one question we are doing from all the types. Okay. So this is symmetry. In symmetry, what we have, two types of symmetry we have. There is a symmetry about this line AB, about which we are finding the resistance. So below section and above section are exactly identical. Okay. So if this is there, about the line about which you are finding the resistance, above and below are similar, then we can fold it. Just fold it up. You can say no, this is and these are parallel. Whatever current goes here, same current goes here. Okay, exactly similar. So you can fold in this one. This is folding symmetry. Folding symmetry about the line about which we have to find the resistance. This is folding symmetry. Okay, so if we fold it, now what's going to happen? 2 and 2, they are parallel now, they become 1. 3 and 3 becomes 1.5, 3 and 3, 1.5, 3 and 3, 1.5, 2 and 2, 1. I am making it, just see. Okay, this is 1 ohm, this is 1 ohm. So they remain same. Okay, now like this, then here and then like this. Okay, so this one is 1 ohm, 1.5 and again 1. Then here it is. So this is also 1.5, this is also 1.5. Okay, so below 1 gone. This is AB. Now what? Still symmetry is there. How? How symmetry is there? Like this symmetry is there. Now I can't say this is folding symmetry. You can't fold it because A and B cannot be at the same point, no? Current has to go from A to B. So this is called mirror symmetry. Okay, this is mirror symmetry. So what happens in this? We say that if suppose from here current is coming like I, here goes I1 and here goes I2. Then mirror symmetry says if here is I1, same I1 will be going here. This is mirror, right? So mirror symmetry says whatever is current over here, same current is here. Same way, here is I2, so here will be I2. Okay, so what happened then? Now you see that if this I1 is here, there is a junction here. Same I1 is passing, that means no exchange of current. And here I2 is going, here is also I2 going. So it means what is happening here, because at this junction there is no exchange of current, then what is the sense of having a junction? So we lift it up. We show it like this. So next diagram is like this here. This is 1, this is 1. Then this is here, then this is here, then this is here. And this junction, no? We make like this. We have broken the junction. Why? Because it's not working like a junction. Why we are breaking? Actually we are breaking in the circuit. No, our solving, we are solving it like this. In junction, we are not breaking in the circuit. Okay? Right. So this is 1, this is 1, it's 1.5, 1.5, 1.5, 1 and 1. Now we know that these two are in series then. So this is 2. These two are also in series. So 1.5, 1.5 is 3. Then 3 and 1.5 are in parallel. And then I don't think any problem is there in this one. Now this one we can do it like this. Just see. Below 1 is 2. Okay. 1.5, 1.5 in series means 3. 3 and 1.5 are in parallel. 3 and 1.5 are in parallel. So there will be a little problem in calculation, right? So if they are in parallel means 3 into 3 by 2, R1, R2 by R1 plus R2. So that is 9 by 2 by, this is how much? This is also 9 by 2. Yes, yes, yes. So this becomes 1. Okay. So 3 and 1.5 when they are parallel, they are giving us 1. So 1 ohm, 1 ohm, 1 ohm, 3 ohm. So 3 and 2 are in parallel now. Okay, so net resistance will be 3 into 2 by 3 plus 2. The net is RAB is 3 into 2 by 3 plus 2. That is 6 by 5, 1.2 ohm. 1.2 ohm. Okay. So this is how it is. This is also 3 and 1.5 are in parallel. So we did R1 R2 by R1 plus R2, and here also the same, R1 R2 by R1 plus R2. So this is symmetry. Both the symmetries I have told you in this. Normally this is very long question, so I don't expect that it will be given, but in this one both symmetries are used, that's why we use it. Okay, folding also, mirror also. Okay, see next. Now we are at Kirchhoff's law, very important. Okay, two laws are there. One is junction law. So what it says that at any junction, the sum of all the currents is equal to 0. Okay. Or it says that sum of incoming currents is equal to sum of outgoing currents. So this is I1, this is I2, there is I3 and I4. So I3 and I4 you can see are going out, I1 and I2 are coming in. So sum of incoming currents means I1 plus I2 equal to sum of outgoing current means I3 plus I4. And first one was what? At any junction, the sum of all the currents is equal to 0. That's also fine. I1 plus I2 minus I3 minus I4 equal to 0. Correct or not? Or minus I3 plus I4. Because these two are coming in and these are two are going out. So convention has to be there. So in coming in we are taking positive. So going out we will be taking negative. Sum of them all should be equal to what? 0. This is junction law. Let's see its applications. It says find V naught. V naught means this. Here potential is given V1, here potential is V2, here potential is V2. We have to find V naught. So this is junction, right? V naught is a junction. The sum of all the currents here should be equal to 0. Right? What we are going to say, we are taking all the currents outside. This is I1, this is I2, this is I3. So we are saying I1 plus I2 plus I3 equal to 0. Okay. We are doing it. Okay, because we don't know the direction, whose potential is more, whose potential is less, we have no idea. We're just taking it. Considering this only is at the highest potential. So if this is highest potential, all the current will be outgoing on. No incoming current is there. So incoming current is 0. That means outgoing currents also will be 0. I1 is what? Potential difference by R1. So V naught minus V1 by R1. I2 V naught minus V2 by R2. I3 V naught minus V3 by R3 equal to 0. Only one unknown is there in this, V naught. Can you find it? Yes, obviously, why not? So R1, R2, R3. LCM R2, R3 into V naught minus V1 plus R1, R3 V naught minus V2 plus R1, R2 V naught minus V3 equal to 0. So this denominator goes that side, becomes 0. Now what we can do here? Simple solving is there. So V naught I can take directly common over here. What's going to come? This plus this plus this. That means R2, R3 plus R1, R3 plus R1, R2. Okay, plus minus R2, R3 V1 minus R1, R3 V2 minus R1, R2 V3 equal to 0. That's it. So this all we will take that side divided by this, that will be V naught value. Done. Kirchhoff's first law, junction law. Okay, second. Okay, see this. Is it Wheatstone-Bridge? R by 2R equal to? No, it's not Wheatstone-Bridge. Something else. Okay, unsymmetrical Wheatstone-Bridge. Okay, fine. What we have to do? Resistance is 1 ohm. We have to find VA. We have to find VB. VA is this, VB is this. Now how to find? Because first of all, we cannot find total resistance over here. We don't know how to find. because it doesn't fall into the normal methods. Okay, it's not Wheatstone bridge. No symmetry. What to do? So we'll go with the Kirchhoff's junction law. We'll apply. Okay, now here is 10. So I can take here 0 and here 10. That much at least we can do. So 10, 10. Here is 10, so that means 10 here. Here is also 10. Same way here 0, so here is 0, here is 0. Now I am applying junction law at A. So VA minus 10. Wait. Okay, what we will do? I1, I2 and I3. Now remember that similar way I have to apply junction law here also. Okay, so what you will do? I1 plus I2 plus I3 equal to 0. What is I1? VA minus 10 by R. Okay, R value is 1, so write 1 only. Plus I2, where is I2? VA minus 0 by 2R, so that means 2. Plus VA minus VB by R, that means 1 equal to 0. Okay, take LCM at the same time. So 2 VA minus 20 plus VA plus 2 VA minus 2 VB equal to 0. So 2 plus 2 plus 1, 5 VA minus 2 VB equal to 20. This is our first equation. Now same way we have to write for B here. So here we will say what? Now when you are doing for this one also exactly in the same way. Okay, maybe this is, let's say, I4, this is I5 and this is I6. So for junction B, again I4 plus I5 plus I6 equal to 0. Okay, what is I4? VB minus 0 by R. VB minus 0 by R. R means 1 plus VB minus 10 by 2R. VB minus 10 by 2R means 2 plus VB minus VA by R. That means 1. VB minus VA by 1 equal to 0. Take LCM. 2 VB plus VB minus 10 plus 2 VB minus 2 VA equal to 0. What we are getting? 2 VB plus VB plus 2 VB. So 5 VB minus 2 VA equal to 10. Equal to 10. This is our second equation. Okay, now both we can solve. These two are equations here. We can solve them. How we can solve? Okay, so I am multiplying here with 2 and multiplying here with 5. So when you multiply here with 2, you see that this becomes 10 VA, and when you multiply here with 5, this becomes minus 10 VA. Add them. So this is 10 VA, this is minus 10 VA. This gets cancelled. Okay, this will be cancelled. What you are getting here now? Minus 4 VB plus 25 VB. So that means 21 VB. Okay, minus 4, 25. 25 minus 4 is 21. And here equal to, this is 40 and this is 50. So that is 90. So VB value you got 90 by 21 volt. That's VB. Okay, then VA will be what? What is going to be VA? Okay, fine. So VA now what? VB value we can put in this equation. Okay, any of the equation. Let's say 5 VA, first one I am putting. So here let's make a boundary. Okay, then. So 5 VA, 5 VA minus 2 VB. 2 VB means minus 180 by 21 equal to 20. 5 VA minus 2 VB equal to 20. That goes that side. So 5 VA equal to 20 plus 180 by 21. The 21 into 20 is 420. 420 plus 180, 600. 600 by 21. But here is 5. So this is 120. So VA equal to 120 by 21 volt. Okay. So VB is 90 by 21 and this is 120 by 21. We got VA also, we got VB also. Now what? I. Okay, I also. Now what we will do is, I am going to write this as a junction now. This is the junction this time. Okay. So if this is a junction, this point we will say what? P. Okay. So for P junction, junction P. Junction P. So VP minus VB. Okay, okay, fine. I2 plus I4 equal to I. Okay, here is I. From here I4 is coming, from here I2 is coming. Clear? So I2 plus I4 equal to I. Okay, so what is I2? I2 is VA minus VP by 2R. Plus, because these both are incoming I have taken, that's why I am taking VA minus VP. If we take outgoing, no, VP minus VA will take. In all other junctions we have taken always outside, outgoing. Here it's coming inside, so that's why I am writing like this. Okay, so VA minus VP, same way, VB minus VP by R. Now VP is what? VP is 0. Okay, VP is 0, right? So VA by 2R, what is VA? 120 by 21, and 2R means 2. So 120 by 21 by 2, that will be 60 by 21, plus VB, so VB by 1, so 90 by 21. So 150 by 21 is I. Kind of tough question, lengthy question, but it is basically I was trying to tell you that how to use the junction law. Let's see loop law now. What says loop law? Now loop law is based on conservation of energy. Junction law is based on conservation of charge. This is conservation of energy. This is conservation of energy, and junction law is based on, where is junction law? Here. Okay, junction law is based on conservation of charge. Conservation of charge. Okay, right. Let's move to loop law again. This is conservation of energy. Now, what loop law says? Loop law says that if suppose there is a closed loop, okay, in a closed loop, potential drop across all elements is equal to 0. All elements means battery, resistance, if suppose capacitance is also included in that. So potential drop across all elements is equal to 0. Conservation of energy. Meaning is, if suppose battery is giving certain energy, that energy is utilized by the elements which are there in closed loop. Okay, so total energy is conserved. Okay, work done by battery is utilized in another forms of energy. If bulb is there, it will give you light. If fan is there, it will give you, okay, mechanical energy, it will be converting it. So whatever energy is given, that is used. So potential drop in a closed loop, potential drop across all elements in a loop is equal to 0. Is equal to 0. Okay. Now, when we are going to apply loop law, there are certain sign conventions that we have to learn. Suppose there is a battery. Okay, battery is like this. So if we are moving from here to here, that means like this. Okay, so we are moving from higher potential to lower potential in a battery. So we write it as minus V because potential dropped by how much amount? V. If we go opposite direction, if you are moving like this, then potential increases by, so we write this as plus V. Okay, in a resistance, okay, if current is like this and it is asked from us that what is VA minus VB, or what is VB in fact, no, don't write VA minus VB here, write VB. What is VB? So we will say that VB is actually VA minus IR. So if you are going through the resistor in the direction of current, potential drops. If you come in opposite direction, that means if suppose, okay, this is I and this is R. Now we are coming in opposite direction like this. So you are coming in opposite direction to current. So current always moves from higher potential to lower potential, but you are moving from lower to higher. So in this case, you will be writing plus IR. Very simple. What we are doing, we are writing VB plus IR equal to VA. That means as you move from here to here, your potential increase by IR. When you go from here to here, your potential decrease by IR. You are moving from VA, so potential decrease by IR became VB. Here, you are coming in opposite direction. Your potential is VB here. When you come over here, it increased by IR, so VA is. These two things you have to remember. Battery, you are going from higher potential to lower potential, write minus V. You are moving from lower to higher, you write plus V. When you are going in the direction of current, you write minus IR. When you come in opposite direction, you write plus IR. That's all that you have to remember in loop law. Okay, let's see. There is a question on loop law. So in this one, you can see that there are two closed loops. One is this, other one is this. Okay, and if suppose I say that from here current is I, then here is a junction. The junction means current is going to split. What we can say, I equal to I1 plus I2. But what we have to find is VB minus VT. Let's see what we can do. Okay, so let's move in this closed loop now. What is that? A, B, C, A. Loop A, B, C, A. Okay. Alright, so let's start from A. So you are going in the direction of current. You have taken direction of current like this. 4 and 2 are in series, so total is 6. You are going in direction of current. So what he will write? Minus 6 I1. Then here also you are going in the same direction of current, minus 10 I1. Then what? You will go in this way. You are moving from lower to higher potential in a battery. So plus 2 equal to 0. Why 0? Because sum of all elements, sum of potential drop across all elements, we said no 0. Okay. So what we are getting? We got current value. So 2 equal to 16 I1. I1 equal to 1 by 8 ampere. Same way here, ADCA. Okay. So here 7 I2 and this is again 5 in series. So 7 I2, I2 goes in here also. So minus 7 I2 minus 5 I2. Then this goes inside here. So plus 2 equal to 0. Here also we got I2 is equal to 2 by 12. 2 by 12 means 1 by 6. But what was the question? Question is find VB and VD. Okay, fine. We'll find VB and VD. VB minus VD, not VB and VD. Okay, so what to do? Consider here 0. Consider here 2. Okay, so VA we are saying is 2 volt and here is 0 volt. Okay, and how much is current through this one? I1. I1 is what? 1 by 8. Okay, now see, I would find VB. I will start from here. Here is 0 volt and I will move opposite to the direction of current. When you go opposite to the direction of current, potential increases. So see what I am doing. VB I have to find. So see, VC plus IR plus 1 by 8 into 10 IR equal to VB. But VC is 0, right? So we got what? VB is equal to 5 by 4 volt. We could have done from here also. Yes, obviously. Here we would have gone in the same direction as current. So then potential would have dropped. So we would have written 2 minus 6I1 equal to VB. Okay, now D. So D also we can go like this, no? Here is what current is coming, 1 by 6. Okay. So VC plus 5 into 1 by 6. So VD equal to 5 by 6 volt. What question is asking? VB minus VD. Okay. 5 by 4 minus 5 by 6. VB minus VD is 5 by 4 minus 5 by 6. Okay. You can solve it easily. 24. This is 30. And this is 20. So 10 by 24. 5 by 12 volt. Okay. Right. Then, now this is, you see, this is open circuit. This is not a closed circuit. But are we going to apply Kirchhoff's law? Yes. In the previous case also we did know. When I was doing this one, I didn't take total element and the potential drop across them is 0. No. I moved it according to the convention. And I got what is the potential here. Same thing we'll do this. Here what question is there? Find VA minus VB. This is VA, that's VB. Okay, so let's start from here. Why? Because current is in this direction, so let's start. How to start in open circuit? We write VB first. This is VB and we start. 10 ampere and we are also going like this only. Okay, so we are moving from lower potential to higher potential in a battery. So what we write? Plus 2. Plus 2. Okay, now we reach here. This is the junction. So from here 6 ampere is coming. So here current is 16, remember. Now you are going in the direction of current through this resistance. So minus 16 into 4, that is 64. Then battery higher to lower, minus 10. Then again here 16 ampere current. So minus 16 into 2, that is 32, equal to VA. Okay, so what we are getting? 64, 32, 96, 106. Minus 106 plus 2, minus 104. So VB minus 104 equal to VA. What we have to find? VA minus VB. Okay. So VB minus VA first of all is 104 volt. So VA minus VB, then what? Minus 104 volt. That's it. If suppose we have to find here also. Suppose this point is D. Okay. And it is asked from us find VB minus VD. Okay, fine. No problem. Find VB minus VD also. Move the same way. We'll come here now. Okay. So VB here plus 2. Now here you are coming. Now here is 6 ampere going like this. Now you are coming opposite to that. So plus 36 equal to VD. So VB minus VD equal to minus 38. Okay. For today's class, that's all. Next class, we will finish current electricity. Okay. So just scan this QR code. It always takes more time, right? But okay, fine. Okay, so note this one and make the notes and keep doing practice. It's a big chapter. Remember that at least 20 marks are in this chapter. So very important. Okay, so that's all. See you tomorrow. Bye bye.